Welcome to the video on analyzing strains in structural components. This topic is essential for an introductory course on the strength of materials in a mechanical engineering program. Whether you're a student or simply interested in the mechanics of engineering, this video has something for you. Let's get started. What is strain? Strain refers to the deformation or change in shape experienced by a material in response to an applied load. When an element is subjected to loading, it undergoes strain. Strain is typically defined as the ratio of the change in dimension, such as length, area, or volume, to the original dimension of the material. The strains can exist in various forms, as detailed next. Linear strain, this is the ratio of the change in length to the original length of the material. It's commonly expressed as epsilon equals delta L divided by L, where delta L is the change in length, and L is the original length. Shear strain is the change in angle between two lines originally perpendicular to each other in the material. It's commonly expressed as gamma equals tan theta, where theta is the angle of shear as shown in the figure. Volumetric strain describes the change in volume of the material due to loading. It's calculated as the ratio of the change in volume to the original volume of the material. Plane strain, a state of strain where all the strains occur in one plane, like the xy plane, and the third direction, z direction, has no strain. So, when are these concepts applied? Plane stress is typically used when you have a thin plate with a length and width much larger than the thickness, while plane strain conditions apply when the thickness of a body is much larger than its other dimensions, assuming strain in the thickness direction is zero. Let's examine strain transformation. In engineering, strain transformation involves determining the strain components in a material when the coordinate axes are rotated or oriented differently from their original position. Imagine we have our original axes, x and y, with strains defined as epsilon x, epsilon y, and the shear strain gamma xy. When we rotate these axes by an angle theta, we create new axes x1 and y1. Now, we aim to express the normal strains epsilon x1, epsilon y1, and the shear strain gamma x1 y1, which are defined relative to the x1 and y1 axes, in terms of the strains associated with the original axes x and y.
We will analyze the deformations in the x, y, and x1 directions in relation to the strains. The figure illustrates the deformation in the x direction and its associated impact on the elongation of the diagonal ds in the x1 direction. If the rotation of the diagonal, ds is alpha 1, we can write the equations alpha 1 into ds equals epsilon x into dx sine theta. This simplifies to alpha 1 equals to epsilon x into dx over ds into sine theta. Similarly, we consider the deformation in y direction and its impact on the diagonal, ds or x1 direction. If the rotation of the diagonal is alpha 2, in this case, we can write alpha 2 into ds equal to epsilon y into dy cos theta. This simplifies to alpha 2 is equal to epsilon y into dy over ds into cos theta. Now, we will consider the shear deformation and its impact on the elongation of the diagonal ds. The increase in length in the x direction is given by gamma xy into dy. If the rotation of ds is alpha 3, we can write alpha 3 into ds is equal to gamma xy into dy sine theta, or alpha 3 is equal to gamma xy into dy over ds into sine theta. Considering the impact of both linear strain and shear strain on the length ds, the total linear deformation can be determined by summing their contributions. Normal strain along the x1 direction is the total deformation divided by the length ds. With the substitutions of trigonometric functions, we can finally obtain the normal strain equation in the x1 direction. By substituting theta plus 90 degrees for theta into this equation, we can find the normal strain in the y1 direction. To find the shear strain gamma x1 y1, we need to determine the change in the angle of lines along ds within the material. To obtain this, we sum all the alpha values that are rotations relative to the x direction, and all the beta values that are rotations relative to the y direction. After calculating the alpha value, we can determine beta by substituting theta plus 90 degrees for alpha in the same equation. However, it's important to insert a negative sign, as alpha is measured anti-clockwise while beta is measured clockwise. The shear strain relative to the x1 and y1 coordinates is the sum of alpha and beta. Finally, the strain transformation equations can be written as shown. There is a noticeable similarity between the equations used for stress transformations and those used for strain transformations as shown here.
Let's now take a look at the material properties related to stress and strain. Modulus of elasticity is the measurement of a material's elasticity. It quantifies a material's resistance to non-permanent, or elastic, deformation. Modulus is defined as the slope of the straight-line portion of a stress-strain curve. Shear modulus, also known as modulus of rigidity, is the measure of the rigidity of the body, given by the ratio of shear stress to shear strain. Bulk modulus is defined as the proportion of volumetric stress related to the volumetric strain of a specified material while the material deformation is within the elastic limit. Another important property to consider is Poisson's ratio. This material property describes the relationship between axial strain and lateral strain when a material is subjected to uniaxial stress. It is a dimensionless constant named after the French mathematician and physicist Simeon Denis Poisson.